let's do another example of polynomial long division. And another thing that is technically not necessary but highly recommended is that if one of your polynomials is missing a term of particular degree, like notice in this case, the first polynomial, 8x to the fourth plus 6x squared minus 3x plus 1, is missing a term of degree 3. What's highly recommended is that you insert what we call a placeholder 0 into the missing slot just for organizational purposes. And technically the polynomial, we don't typically write it using that missing term, which, since there is no term of degree 3 within this polynomial, usually we don't write it, but it's helpful for the purposes of organization. And you'll see as we progress why inserting that is quite helpful. But let's do it a little bit faster than the last one. And again, we'll focus on the whole match, multiply, subtract goal or strategy for dividing polynomials. So we always begin by trying to match the leading term of each of the polynomials via multiplication. So my divisor consists of 2x squared, and my original polynomial is 8x to the fourth. And my goal is always to match the leading terms from the left to the right. So 2x squared, what multiplies into 8x to the fourth? Well, that would of course be a coefficient of 4 and a polynomial of x squared, because 2 times 4 makes 8, and x squared times x squared makes x to the fourth. Then once we match, now we're going to multiply this monomial to the entire divisor. So 4x squared times 2x squared minus x plus 2. Again, we must use the distributive property. This 4x squared will multiply to all, because when we're multiplying a binomial by a trinomial, every term must multiply by that. So this would leave us with, well, of course, 4x squared times 2x squared would be 8x to the fourth. 4x squared times negative x would be negative 4x cubed. And you could see why inserting the placeholder 0 was helpful there, because it allowed me to, not be missing a term once 4x squared is multiplying into the divisor. Then 4x squared times 2 would be plus 8x squared. And everything is, nice and lined up. Each term is matched up with its like terms. And again, what we do next is subtract. So match, multiply, step 3 is subtract. Or as I said in the last video, the shortcut is to change each of the signs and add, because changing all of the signs and adding is equivalent to subtracting by distributive property, distributing the negative. And again, as I recommend, adding is just easier. So 8x to the fourth minus 8x to the fourth will completely cancel and eliminate, as it always should if we're doing it correctly. Then 0x cubed plus 4x cubed would be 4x cubed. And 6x squared minus 8x squared would be negative 2x squared. Then we drop the next term and repeat, rinse and repeat. Match, multiply, subtract, match, multiply, subtract, and so on. And again, we're always only matching the leading terms. So 2x squared will match to 4x cubed by plus 2x. 2x goes into 2x squared to make 4x cubed. 2x multiplies into minus x to give negative 2x squared. And 2x goes into 2 to make 4x plus 4x. Again, we would then change the signs and add, which is the same as subtracting. And that would leave us with cancel. In this case, the second term actually cancels, which is not very common, but it can happen. And so again, that would leave us with 0x squared, and negative 3x minus 4x would be negative 7x. And bringing down the next term would leave us with plus 1. And again, we keep match, multiply, subtracting until we basically can't go any further. And one thing that's different about dividing by polynomials is sometimes our remainder could involve more than just a number. Like when you're dividing, 57 divided by 13, the remainder is always just a singular number. But sometimes, because again, if we were to think about, well, what would I do next? I could try to match, multiply, subtract once again. But notice that 2x squared, it's impossible to match into negative 7x, not because of the coefficient. Technically, you can match any coefficient with any other coefficient. But x squared cannot multiply by anything to get to x. So at the point in which the degree of whatever we have left over from our subtraction process is less than what we're dividing by, that's the point in which we can no longer progress. And that gives us our remainder. So in this case, our answer, or again, the quotient, is going to be what's above the bar, and our remainder is going to be what's below the bar at the end. And the remainder could involve, it could be an entire polynomial function. And then to answer the division problem, if we were trying to figure out, well, what's the answer to the original question? Well, it's always equal to the quotient, because that's like what passed through the division. It's kind of like the whole component of my answer. And then it's always plus the remainder over the divisor. So the remainder in this case was negative 7x plus 1. And our original divisor was 2x squared minus x plus 2. And again, this is just like when you're dividing by a mixed number. When you're dividing by two numbers and you get the remainder, typically the way we write it is, well, the part that came through, like just, let's do a simple example, because I wanted to explain the structure of the answer, because I think I forgot to in the last video. But, say we're going to do 42 divided by 13 or whatever. Or, I don't know, let's just make the numbers even easier. 5. 5 goes into 42 8 times. 8 times 5 is 40. Match, multiply, subtract, remainder 2. And we can't go any further when it comes to numbers once our number beneath the line is smaller than what we're dividing by. And how do we write our answer? Well, 42 divided by 5, we conclude is that the answer is 8. But, we could write that as R2, but that's not a common way of writing an answer, right? So one way we often write it is by using a mixed number notation, because what we have is 8 and 2/5, because the 2 is kind of like the component that did not pass through the division problem, which was the fractional remainder. But this is basically the structure that I did here is exactly the same, and that's why I bring back up the process of division. When 42 divided by 5 is 8 and 2/5, or that's equal to 8.4 with decimals. But as I said, there are no such thing as decimals with polynomials. You can't make a polynomial decimal. You can have your coefficients be decimals, so I'm not trying to say you can't use decimals with polynomials, but there's no such thing as x point x or x.5, right? Just, it doesn't make sense. Anyways, but basically, again, we get the quotient, which is always the part that comes through, and then it's plus the remainder divided by the original denominator. And so that's exactly the same structure when it comes to writing the answer to a division problem. Is we have the quotient right there, we have the remainder on top, and the divisor on bottom. So, again, this would be one way we could write our final answer. And basically, like in the last one, since we have a remainder, that implies that these two polynomials were not divisible, because the answer that I get is not whole. Just like how, 42 and 5 they're not divisible because we get a remainder. And when we do have numbers which are divisible, we get a zero remainder. So what that produces is basically no fractional component. And the same thing will be the case if we get a zero remainder. What would happen is we're just left with a polynomial, and we get something which one polynomial which perfectly goes into another. And we're going to talk a lot about how that connects to factoring when we get into chapter 5. So in chapter 5, we're going to talk a lot about different methods of factoring polynomials, but also how you can use division to factor, which is something that's less commonly discussed. But anyways, summarizing, we have our answer to our division problem. In the next video, we'll do one more example, and that's it for this one.